Hello everyone, this is lecture 17 for the mathematical physics. In the last lecture we studied about the eigenvalues, means we saw some examples and find out how the eigenvalues and eigenvectors, and practically we have seen, means in the theoretically with examples we have seen how to calculate values. Okay, now there are some theorems related to the eigenvalues and eigenvectors. Okay, so and there are some properties also. Let's see them. So first one is Cayley-Hamilton theorem. So what this theorem says, every square matrix satisfied its own characteristic equation. Okay, so what is characteristic equation? You know that when we write a minus lambda I, then solving the determinant of that, we get the characteristic equation. That is in the polynomial of lambda. Hope you remember from the last lecture. Okay, so let's see an example. A square matrix A, that is Aij, order of n, has its characteristic equation of the form. This type of form we get after solving the determinant. If it is n into n order, then maximum power of lambda will be n, and it will be like this: lambda n minus 1, lambda n minus 2, and this. This type of characteristic equation we get always. These are some constants. Okay. Now, what this Cayley-Hamilton theorem says, that this equation satisfies means every square matrix itself satisfies this equation, means lambda is variable. So if you put the matrix A here, then it will satisfy this equation. So just put the A in place of lambda. So A naught an plus a1 an minus 1 a2 an minus 2, and this will also be means it will equal to 0, and it will satisfy this equation. Okay, now what is the use of this Cayley-Hamilton theorem? Means okay, we get that this A matrix satisfies this equation. Now what? So you can find the inverse of any matrix using this Cayley-Hamilton theorem. So how? You can find the inverse of a matrix by using the theorem. Let's say A is matrix this. Now characteristic equation can be written by A minus lambda I. So this, after solving this determinant, we will get this. This is the characteristic equation. Okay. Now in place of lambda, if you put A, this matrix, this will satisfy this equation. That is Cayley-Hamilton theorem. So let's place, in place of lambda we place a square minus 3a minus 10, and now it's a number, so we have to multiply I, identity matrix, to make it a matrix. Then only we can algebraically add and multiply them. Okay, now what you have to do, just put this 10i this side and a square minus 3a this side, and I will be 1 upon 10 this. Okay, I just rearranged this equation. Now multiply with A inverse on the left hand side. So A inverse I will give A inverse, and A inverse AA will give you A, because one A inverse A will turn out to be I, and IA will be A. And here A inverse A will give you I. So this will be resolved to this. A inverse equal to 1 by 10 A minus 3I. Now just put here in place of A this matrix, and you will get the A inverse. So that's how you can use this theorem to find the inverse of a matrix. Now same you can apply for this example and try to solve it at your home. Okay, so you can find the A inverse, means first find this characteristic equation, then in place of lambda put A, and then multiply with A inverse, and then you can find the A inverse in terms of A. Okay, so just remember this. Now there are some properties of eigenvalue. What are they? Consider real invertible n into n matrix, okay, M, has eigenvalues lambda I, means I1, 2, 3. Any number of eigenvalue can be possible. If it is n order, then it will be n eigenvalues, and there are corresponding n eigenvector also. So xi denote eigenvectors, lambda I denotes eigenvalues respectively. Now for any eigenvalue and eigenvector, we can write axi equal to lambda I xi. Okay, so what is the property? Property is, if we write A inverse xi, then it will be equal to 1 upon lambda I xi, means the eigenvalues of A inverse will be 1 upon lambda I. Okay, so just remember this. This is very important relation, that the eigenvalues of A inverse will be 1 upon lambda I, and eigenvectors will remain same. Okay, now we have some special matrices, and let's see the values of eigenvalue, where they lie for different type of special matrices, like orthogonal matrices, unitary matrix, skew symmetric, symmetric, Hermitian, skew Hermitian. For them, where the eigenvalues lie, you should remember those things. Okay, the question will be asked directly and you will be able to solve them if you know this. So if this is an imaginary axis and this is real axis, okay, then the eigenvalues of symmetric matrix will always be real. Means symmetric matrix eigenvalue always lie on this axis, okay, and for the skew symmetric eigenvalue always lie on this axis, means they can be imaginary or zero, and for the symmetric matrix they can be real, okay, and for the symmetric the same for the Hermitian matrix, and what is for the skew symmetric will remain same for the skew Hermitian. Now what are symmetric matrix? When A transpose is equal to A, and for skew symmetric A transpose will be minus A, and same for skew Hermitian, the A dagger will be equal to minus A, and A dagger is nothing but complex conjugate, okay, means conjugate and then transpose will be skew Hermitian, means that will equal to minus A, and for Hermitian A conjugate transpose will be A, okay. So these both have the same property, these both have the same property, means for the eigenvalues where they will lie. Now we have two special matrices, that are orthogonal and the unitary matrix. So what are orthogonal matrices? Orthogonal matrices are those where A transpose is equal to the inverse of A, means A transpose A equal to I, okay, and for the unitary matrix A dagger should be equal to A inverse, okay, means A dagger A equal to I. So where their eigenvalues lie? Eigenvalues of orthogonal matrix are real or complex. They can be both real or complex. If they are complex, then they will be in always exist in pairs and have absolute value 1. Means the absolute value of eigenvalues will always be 1. Okay, and they can be complex also and real also. If they are complex, they will be in pairs. Okay, like 1 minus 3 iota and 1 plus 3 iota, like this. Okay. Now for the unitary matrix, the eigenvalues lie on this whole circle, okay, and its absolute value will always be 1, okay. So these both have the same property, these both have the same property, these both have the same property. Just remember these, that where their eigenvalues lie. Now we some questions are asked based on these properties also for the eigenvalues. Means just remember this line. Now there are these three properties, that sum of all the eigenvalues equal to trace of A, you know that. Now trace of A square matrix will be equal to sum of the squares of eigenvalues, and trace of A cube will be sum of cube of eigenvalues. Just remember these all three, they are very helpful. Let's see one example based on these properties. Given a 3 into 3 matrix M has trace M equal to 6 and trace of M square 26, trace of M cube equal to 90. So which are the possible eigenvalues? You have to find which is possible eigenvalues for which satisfies all these three given equations. Okay, so if you see in the C option, then for trace of M cube, the sum of cubes of eigenvalues should be equal to 90, and sum of square of all the eigenvalues should be 26, and sum of all the eigenvalues should be this. So only this satisfies these equations. Okay, just you can put the values and you can find this will be the correct answer. Now there are one more question. One of the eigenvalue of the matrix e to the power a is Ea, where A matrix is this A00, 00A, 0A0. Now find the product of other two eigenvalues of Ea. So it is 3 into 3 order, so one is given, so other two we have to find the product of other two eigenvalues. So we know that the product of all the eigenvalues equal to determinant of that matrix. Okay, so if eigenvalue of a matrix this, so what is the determinant of this matrix is lambda 1, lambda 2, lambda 3 will be determinant of Ea, and you know that from the property of matrix I already told you this is equal to e to the power trace A. Okay, now trace A is what? The sum of diagonal elements. A plus 0 will be A, so it will be e to the power A, and 1 lambda is given, that is e to the power A, so put it here, it will cancel out, and other two product will be equal to 1. So that's how you can solve. So just to use these properties and try to solve more and more problems based on these properties, and you will be able to solve any type of questions. Now Determinant of orthogonal or unitary matrix will always be equal to plus minus 1. Just remember this. Okay, now let's see some transformation equations of orthogonal and unitary matrix. What are they? Let A be a orthogonal matrix. I told you already what are orthogonal matrix. A transpose A equal to I means A transpose should be equal to A inverse. Okay. Now what are orthogonal transformation? Means any vector x, that is column vector, any column vector x, if we operate this orthogonal matrix on this, then the new matrix will be get in y. So this is the transformation. Okay, orthogonal transformation. We call this orthogonal transformation of this vector. Okay. So what are the properties of this? This transformation preserves inner product of vector A and B. What this line means if you find the orthogonal transformation of A and you find the orthogonal transformation of B, then A dot B will remain same, means inner product of A or B remains same as the transformed version. Okay, so what is the transformed version of A? That is U. For B it is V. So U dot V will always equal to A dot B. That is the probability. Means inner product of A dot B will be preserved. Okay, and you know how to find this inner product. It is transpose of first and this second. A transpose B equal to U transpose V. Okay, so these are easy. So just remember this, that orthogonal transformation preserves the inner product. It also preserves length or norm of the vector. So if you find this transformation is this U, so if you find the norm of U will be always equal to norm of A. So it preserves the norm and length of the vector. Okay, I hope it is clear to you. Now there is one more property. A real square matrix is orthogonal if and only if its column vector, means any square matrix, real square matrix is orthogonal only and only when it's all the column vectors are orthogonal to each other. Okay, and all the row vectors are orthogonal to each other. Only then we call that square matrix as orthogonal matrix. Means I can take an example, or you can just see this. If there are A1, A2, A3 column vectors or row vectors, then A1 dot Aj, that is inner product, will equal to 0 if they are different, and that will be 1 if they are same. That is orthogonal property. So you will better understand by an example. This is a matrix. Now these are the column vectors. So these all three are orthogonal to each other. Only then this whole matrix will be orthogonal. So A1 is this, 2 by 3 minus 2 by 3, 1 by 3. A2 is this, A3 is this. Now A1 dot A2 should be 0, A2 dot A3 should be 0, and A1 dot A3 should be 0, and A1 dot A1 should be 1, A2 A2 should be 1, A3 A3 should be 1. Okay, and if you find them, they will all satisfy these equations. That's why we can call this A as orthogonal matrix. Okay, now let A and B are two vectors, and we find the orthogonal transformation of A by operating this whole matrix on this and whole matrix on this. So we get this U vector and V vector. Now you can see that you can calculate that A dot B came out to be 5, and if you find the U dot V, and it will remain the same. So this proves that orthogonal transformation preserves the inner product. Okay, and same you can see that length, that is A transpose A, is equal to root 14 and it equal to norm or length of U also, and B root 6, and it is same for V also. Means it also preserves the length or norm of the vector. Now the same equations and same all these transformation are valid for unitary matrix also. We will study them in the next lecture. Okay, and we will see some examples of unitary matrix also. Okay, thank you everyone.